So, hi everyone, good afternoon, and I'll be talking about parallel computing, continuing on from last week's discussion on OpenMP. We're going to look at message passing interface, or MPI, today. And I'll also end with basically a hybrid approach between the two as well. So, as many of you probably already know, today's computers are essentially clusters of a lot of multi-socket nodes. So each node itself, like if you look at Expanse, for example, you have 2 sockets and 64 cores on each socket. So you end up with quite a lot of cores sitting on a node, and then they're all interconnected with some kind of high-performance interconnect. Usually it's InfiniBand in these days, but there are other options. And the other thing to keep in mind is a lot of the memory access is non-uniform. That is, you'll have a different memory access pattern, levels of memory access, even on a single node or even on a single socket, right? So with these large number of core counts and also trying to scale to multi-nodes, you need an approach that's scalable and parallel to unlock the performance that's available in the current day systems. And that also brings into play network topologies, and you'll also see that most systems will have a high-performance network like InfiniBand or like a specialized interconnect like the Craze have. And also in a lot of cases, differing architectures even on the network side. So you could have a mesh kind of network or a torus, or sometimes you have a torus of switches instead of just torus of nodes, essentially. So you you can have a complicated multi-level setup in the network itself. So on Expanse, we have a factory kind of setup, but it's oversubscribed between ranks. Between racks. And a lot of times, so what you have to keep in mind is, what's the kind of bandwidth you get going out of a node and at a system level. And it gets important as you start scaling up. So So parallel computing essentially involves executing instructions concurrently on physical resources. So it's not time slicing. You're at any given time, you're using all these resources that are coupled to solve a particular problem. Now, the benefits, of course, are you're scaling up in memory, storage, and performance as you bring in all the resources. But there's a cost to that. You have to coordinate all the tasks and resources and also be able to use them efficiently, right? So if you scale out to a lot of nodes and then they're all waiting on each other and you're spending more time waiting than computing, then that's a problem. So all kinds of considerations. And in terms of computer architectures, there are lots of classifications. You have the single instructions, single data, like basically serial setup. You have a single instruction, multiple data, processors running the same instructions, but operating on different data sets. And then multiple instruction, single data, and multiple instruction, multiple data, which is the most common thing. So every processor might execute different instructions, and every processor might work on different parts of data. And you can have this be synchronous or asynchronous, and sometimes it's not even deterministic. And most of the big systems are in this category right now. So there's also, different execution models. You looked at the shared memory approach last week, where basically all the communication is happening through the shared memory. And what we are looking at today will be a distributed memory model where each task has its own memory space and there's no overlap between them. and you have to explicitly exchange messages when you are trying to communicate. And then there are different execution models that are kind of dependent on this as well. So the fork join is what you saw last week. And what you have now is like a single program, multiple data kind of setup. So the parallelism is enabled by decomposing work. And so you're giving chunks of work to different tasks, and these tasks can have dependencies. So you might need some kind of synchronization or transfer of data between them. So message passing interface is basically a low-level message passing abstraction. So it's an API specification. So what it does is standardizes a bunch of these communication routines and makes it easy for code development so that users can develop code based on the spec. And then on each of these machines, you can have an implementation, and you might have multiple implementation on a machine. For example, on Expanse, we have Mpi 2, Intel Mpi, and OpenMPI. And the nice thing is that there are high performance implementations available on most systems, and the user at some level doesn't need to know how MPI is doing the transfer under the covers, because the API is the same. And so you may have an MPI that is tuned to the particular hardware and set up to optimally use whatever complex network is behind it. But then your program is just calling the same MPI API. So like you might say, oh, I want to do a reduction operation. And the MPI implementation on the backend is taking care of what is the most efficient implementation on a particular machine. So you'll see there'll be tunable parameters in Mpi or Intel MPI that might be very specific to the system. And then, most MPIs also give you some control on the tuning parameters as well. So you can, if you're informed, you can do those sort of things. And there are all types of MPI API calls available. So mostly you'll be using point-to-point communication, so one task to another, specific task pairs. There are all kinds of data types, and also you have collective operations where all the processors might be talking to each other. And then similarly, you have parallel I/O and different kinds of communications where you do one-sided communications and so on. So we won't go into like a super detailed look at all of these, but just know that there are lots of routines available. Like we might look at 20 of them today, but they might be 100 plus available. So any basic MPI code will have like a structure like this. You'll have an include file which has a lot of the variable definitions and things that are MPI specific, and then you may have a little bit of the code that is a bit serial part of the code, but it's usually not much. And then there is an MPI init or initialization call. You have to remember the same executable runs on all the nodes, and all the tasks are running basically identical things, except there are pieces or routines in that you can use to figure out which task the particular instance is running basically. So you have the MPI rank call, which basically identifies the process. So basically, based on this rank, or which MPI task it is, you can do different pieces of the work. So you can break up your like say you have a 2D domain that you're solving on, you can break it up based on the rank. And then, as I mentioned, like you might need to do communication between these processes, so that you'll have some communication routines, and you might have some more parallel code going on, and then communications again. And the end of the code usually has a finalize. And today I'm going to, in the examples, look at some of these things in detail so that you can see how you can do domain decomposition, for example. So I stuck all the examples on expands, and you can copy them to your home directory. So just copy that whole directory. And I also put all the commands that I'm going to be using in the in our session today. For the hands-on pieces in the GitHub repo, and there should be a run_commands.txt so that you can just cut and paste from that file instead of getting it from the presentation. Because sometimes what happens is PowerPoint presentations or PDFs, the cut and paste, might convert the dash into a long dash and cause problems when you try to use the command as is. So I have the text file with all the commands there. So we'll start off by a simple Mpi code that is going to compute pi. It just initializes Mpi, finds the number of tasks, and the way we are computing pi is just using an integral, and we are using a set number of intervals. And we basically say, hey, if I have to sum across 128,000 elements, so you think about it as you're integrating from, say, 0 to 1 on a particular function. You break that up into 128,000 intervals. You can always do the sums for different sections separately, right? And then at the end of the code, you can do a reduction operation that sums all the tasks together to get the final integral. And so it's a very simple code, but it illustrates all the pieces that you would see in a Mpi job. So this is the code itself. It's a C code. So basically, it's taking an argument. Basically, how many processors you have, and so you do the initialization. The COM size tells basically returns the number of processes the Mpi was launched with. So if you say Mpi run with 16 tasks, this will return 16. And then the COM rank, as I mentioned, gives the ID of the particular task. So and then I have some printfs which are based on the rank, like just saying how many tasks are there. So if I didn't put like a qualified, a check here, conditional print, every task would print the same thing. Then if you ran with 32 tasks, you would have 32 messages saying number of Mpi tasks. And since we just need to know the total once, we just print the rank out from rank 0. So you have to remember the task mapping starts from 0 with all the Mpi jobs. So you can see how we are dividing up the space. So we have found the total number of local intervals. So remember, we had 128,000 total. And say you ran with 16, you can just divide it by 16, and that would be the number of intervals on each Mpi task, right? And then based on that and the global index that you can calculate based on the local index times the rank plus I. So it kind of, say you're on rank 2, you would have your local index will still start from 0, because remember, each task is running the same code. So the loop is going to look the same on each task. So it's our job to figure out what the global corresponding index is based on the rank and the local index. So say you're on the second processor and you have 16,000 elements per processor. So then you can say, well, the first task will have 16,000, the second task will have 16,000. And if you're on task 3, then you start from 32,000, right? So that's what's happening here. So you can imagine if you have 0 to 1 broken up into 128,000 intervals, you can now figure out where globally the particular location is. So once you have that, you're essentially finding the function value based on the global location, right? And we just add them up. So now at the end of this step, before the reduction step, what you will have is on each task, there'll be a sum of the local integral, right? So you're, as you can see, I have the pi local here that I'm adding in a loop that's happening on every task. So once you have the sums from every task, this reduction operation basically adds all of them up and gives you the final pi value. And I'm normalizing it with the number of intervals, I think. So, but other than that, this is basically doing what you would do on a single task. You just broke up the domain so that you do pieces of it across all of them. So in terms of how this gets laid out on a cluster, you can have, so if you look at the function call before, it talks about this Mpi com world. Com world essentially includes all the tasks in an Mpi launch. There are sophisticated things you can do by creating your own subgroups and communicators and everything, but we don't need to go into that today. But the com world basically has all the tasks, and then these tasks could, I mean, they could all be on one node if you have enough cores, or it could be spread out, and that's kind of showing you how it might get laid out on a cluster. So just to go over the minimum functions that you need, like the MPI init, it initialize, it has to be called once in every MPI program. Com size, as I mentioned, tells you the total number of tasks in the communicator. And the default communicator includes all the processes. And then the rank ID comes from this MPI com rank and so on. So to run this job, all we have to do is compile and submit that batch script that's there. So I'm going to stop sharing and log into one of my nodes. And hopefully I can, and you can follow along if you, but all the files are available on the system. So if it's going too fast for you, you can do this on your own time and ask us questions offline if needed. So I'm going to log in out here and share the screen. Hold on a second. I have two-factor setup. So all right. So let me share my terminal now. So everyone can see my terminal?
Yes.
Okay, great. So I had already copied this directory. So I'm going to go to the simple and just set up my modules. So the first thing you need to do is set up your compile environment, right? So all I'm doing here is resetting the modules, loading a GCC compiler and loading Mbapich2. And if I do a module list, I'll see that I have those two compilers loaded now. And MPI CC is the wrapper that goes around a GCC compiler to enable the MPI part of it to be compiled. And then if you look at the job script, you'll see, and since you've been running a little bit all these weeks, this should be all familiar to you in terms of the accounts and everything. And this account you will have to change to your number. I think I already changed it in the default for the class, but if it doesn't work, just make sure you use the account that works for you. Other than that, you shouldn't have to change anything else. And you can always change this account on the command line, and which I will have to do now. So you'll see that all of this is very similar. So I'm setting up the run environment. I'm loading the same modules. And then I'm doing an S run to launch the MPI job. You can also do MPI run, but and then I'm saying this MPI equals PMI2 is kind of the interface to Slurm for MPI. And then we are running with 16 tasks and running this Pi executable that we just compiled. So if I do an ls-lt, you can see this just got compiled. Right? So what I'm going to do is put my account in here, but you will have to use yours, which is, I think, SDS 173, if I'm not mistaken. So once it's running, and I ran this yesterday, so that I don't have to wait for the job to finish, but you'll see the output. And this was a simple case where, if you remember the Pi program, it says hello from each task, and it also prints the total number of tasks, right? So if I go back to this terminal here, you can see basically each task is writing out the MPI ID that starts from 0. And notice it's not in sequence because each task is just printing it out, and it might come out in any sequence. It's pretty random which sequence it comes out in. And then you can see that the Pi output is in the middle of all this. So that's the simple code. And I'm going to go back to my presentation. At some point, I might just share the whole screen. That might be easier, maybe. Let me do that. So you can see my desktop now, right?
Yes.
Okay, great. So I'll go back to this. Okay. So so we just did the first simple compile and ran the code, right? So now in that case, the only communication was at the end of the job where we just sent the sums from every task to one of the tasks and then printed it out. But before we go into the collectives in more detail, the first kind of simplest kind of communication is the point-to-point communication. This is basically passing data between two and only two MPI tasks. And typically one task sends the performs the send operation, and another performs the matching receive. And there are lots of different ways you can do the send, which synchronized and also like whether it's synchronized or not, or also like what kind of buffering we want to do and so on. And any type of send routine can be paired with any type of receive routine. And MPI also has routines to kind of probe the state of the messages, and also routines that wait on something to finish. So just a quick talk about buffers. So you have basically in an MPI implementation, you have application level setup where basically you have data that the application has that it wants to send to some other task, right? You also have system buffers on each that are associated with each task. And you can also have user managed buffers if in the more complex MPI implementations. But in all cases, like essentially the buffer is where the data in transit is managed. So like say task 1 is sending to task 2, it doesn't send it directly to the other application. Usually what happens is it goes to a system buffer, and then it's read from the application on the other side. Now, some of these one-sided communications are the ones that directly write into buffers, but I'll leave that alone for now. So if you have a blocking send receive routine, this is kind of the simplest thing. The blocking send will return only when it's safe for the application buffer to be reused, which means if you had something in the application that you wanted to send, it will wait for acknowledgement that the receive buffer has all of the data before it changes anything on the application side, because otherwise there's going to be a problem, right? Like if you send something partially and then change the buffer before the send is complete, then that's going to be an issue. So in a blocking send, it will basically wait for that receiving process to basically confirm that the buffer there has the data. It's synchronous if there's confirmation of safe send, and asynchronous otherwise. And then the blocking receive returns once the data is in the application buffer, so that you can the receive buffer can be used by some other thing. So this is kind of the slowest thing, because everything is going to wait for confirmation. But it's also kind of very safe, right? Like nothing moves along till there's confirmation that either it's been sent or received in the right buffers. So the call looks like this. So this is a code snippet from the blocking send receive example that we will probably run in a second. But what we are saying is, hey, if my ID is 0, which is task 0, do a send. We are basically setting up the send buffer here, the whatever we need to send. And so the send call will usually have the buffer size, the send, the name of the variable, and then the buffer size, the type of variable it is. So we are saying it's an MPI float here. And also the destination. So we are saying send it to task 1. You can tag these messages, and also the com world, which is defining the communicator. And we use com world by default for everything, unless you want to be sophisticated and set up different communicators. That's very rarely done. And then if it's task 1, there is a receive receive call that is corresponding to this send. You'll see that there's a receive buffer size, which should be the same size, and then the MPI float, and then you're saying you're going to get it from processor 0, and then the tag and that. So, and then once this is done, we print out the receive buffer. So all the point-to-point examples are in this directory. So let me get out of that and go to the point-to-point directory. And we are going to say, let's compile this. And I'm not loading the MPIs again because I already did that, but you can load it if you want to. And then submission is the same, right? And I think I have output of this too, so I'm going to show you that. So essentially what you see is the receive buffer got the right numbers. So let me check if there are any questions. I see that Cindy put the run command. Thanks. So now the thing is, as you can see, these are blocking sends and receives. So you can imagine a case where you set something up where the processes are waiting on each other and it never finishes, right? So for example, take this code snippet, right? My ID is 0. You say, hey, send something, and then and then you put a receive for the other side, and then you say my ID equals 1, send something, and put a receive that's corresponding to that. Now what's happened now is that they're going to wait for each other, because this send will never complete, because we said synchronous send till the receive is posted, but the other processor also did a send and it's waiting on a receive. So they both will never get to the receive, and they'll basically deadlock and never finish. So that is this example, and I'm not going to run it, but what you'll see is you can compile and run the thing. The amount of data we are sending is so small, it should take less than a second, but this code will hit the wall clock limit, which is 1 minute in the script. And you'll see something like this that says canceled because it's hit the time limit. So there are lots of fixes. One simple fix is, just change the order. If one of the receives is posted first before the send, then they'll both complete, because it'll clear the other send, and then that receive will clear this send, and it should be good. So that's one way of doing it. And you'll see in that deadlock fix one example. And I have all these in the run command, so you can go try this out yourself to see how these things go. The other option is to have non-blocking MPI send and receive routines. So let's talk about those. So these return before there's any confirmation of receives or completion of the actual message copying operation. So the routine will simply put in the request to perform the operation, and then there's a MPI wait routine that can be used to check status. And you can block till the operation is complete. So that way, this non-blocking approach basically allows you to compute things that can continue without the communication happening. Like, say you're doing a PDE solver, and you really need to exchange only the boundary points between each step. So what you could do is at the beginning, do the first step and then send the boundary points first, and then do the rest of the computations independent of that. And then before you go to the next step again, you do the wait check to see, hey, did the other boundary transfer complete? So that way you can overlap most of your compute, most of your communication with compute. So it's going to be very efficient. So this is one such example of a non-blocking. So again, we are starting with the source, and now instead of the S send, we have an I send, which is the non-blocking. And now you'll see that there's an extra request variable here. And then there's a receive that has non-blocking receive also, basically, which has that extra thing. And then you have an MPI wait call on this request and status. So this will only exit once the request is complete. Now this way, basically you can progress to the next step easily, and the wait ensures that you don't reuse any of the variables before they are before the send and receive is complete, right? So going back to our deadlock example, you don't have to change both. You can just change one of them to as non-blocking, and then you have the receive and synchronous send. That's fine, because this is non-blocking. This will return immediately and go to the next line, and that should fix your non-block. That should fix your deadlocking issue. So we just looked at different ways of getting around that issue, basically. And again, compiling and running is similar to what we did before. So there are lots of options on the point-to-point routines, mainly to do with what kind of buffering you're doing, and if you're doing one-sided, and also all those sort of things. So in a one-sided communication, you can directly write into the other node without having to go through the buffers. But I'm not going into those, but I have links to some nice MPI tutorials which are much longer, and you can find all examples for those sort of routines and play around yourself, I think. Now, collective routines. This is basically routines that involve more than two processes. And typically this depends on the communicator. If you have a communicator that is a COM world, it'll involve all the tasks in your MPI job. So there are several kinds. There are some that are synchronization routines. All processes in the group and communicator wait till they get synchronized. Then you have the data movement, which is send receive data from all processes. So you broadcast, scatter, gather, all to all kind of routines. You can actually do some collective computation in your operations. So you can say do a reduction, like find the minimum, maximum, or add all of them or multiply all of them while you're doing the reduction. And what I want to say is you can definitely implement all these on your own using point-to-point routines. But just have to remember that a lot of these MPI developers have spent years optimizing and also are very closely following the architectures and the network advances and kind of keeping up with all that. So if you write your own, you'll probably miss all those optimizations. So, but it's a lot of the algorithms that are used are public, and you can see how they do those collective operations. And you can do both the computation and data movement combined also. So we'll start with a synchronization example. Our actual simple Pi program, I had thrown in a synchronization, even though it wasn't needed. But there was a code piece that said MPI barrier, right? What this means is this will block till all the tasks get to this point. So say you want to make sure that every point in your domain is updated before you go to the next step. And you don't want to accidentally start running the next step on parts of your domains and not on the others. You can have a barrier to kind of synchronize all of them. In general, barriers are not a great idea because they can be pretty like you might miss like MPI imbalances and things and get lots of communication delays because everything is waiting on a barrier. There are all kinds of collectives, as I mentioned. So some examples I borrowed from one of Mary's slides from last year, I think. Basically, you have a broadcast example where data in one place, one rank is sent to all the ranks. There's a scatter where you say you have an array, you send pieces of it to different ranks, and you can have a logical way of doing that. Gather is the reverse of that. You get pieces from all the ranks and put it all together. And then you have the reduction, which is what we saw with Pi. We saw the reduction operation of summing up everything, right? So that's what we were doing in that example. So some code snippets showing collectives. So again, we are saying, hey, there's a source, and we're going to, this is a broadcast example. So we are basically saying, well, we have a buffer that we need to send to all the nodes. So you do a MPI bcast call, and you have a buffer, you have a count, and you have the type of variable that you're sending, that's an MPI integer, and the source. And if you compile and run this code, you'll see basically every processor will have the value now. This is often used in codes where, say, you have parameters that are needed by all the tasks. You read it in task 0 and then send it out as a broadcast to all the tasks. The other thing you can imagine is, say you're trying to find the maximum error or minimum error everywhere, and then you need to send it to all the tasks. You can do that. Although there are routines which do both together, like I mentioned before. So the reduction is basically, again, a collective that does some operation with data from all the tasks. So in this example, what I did is I added 1 to the my ID, which is the MPI rank in this case. So if the MPI, say you have 8 processors, it goes from 0 to 7, right? So this will go from 1 to 8. And then what I said is I want to reduce that value I'm calling the output, I'm going to stick in a I factorial. And I'm sending it to, I think, task. I'm basically sending one instance and sending it to one particular task, the root task. And it's the size is a MPI integer, and size is 1, and it's a type MPI integer. And MPI underscore prod is the operation I want to do, which is basically a product operation. So what it will do is basically multiply the numbers from all of them. And in this case, since I just added 1 to the MPI ID, this is going to come back with a factorial, which is what this is doing. But this is an example of a reduction operation that is doing some compute at the same time. Now there's the concept of all reduce, where basically you do the reduction, but you send the info to all the processes. So I do basically a reduction. I'm just doing a random number and based on the ID, and then doing a bunch of I mean, basically taking that local value and reducing across the whole thing. This time I'm doing Mpi Max, which is finding the maximum number in all cases. And again, it's an integer. So and then I'm adding another thing called, if Imax is equal to the Imax log, then I can say, hey, the maximum is on this task. So essentially, we'll find out where the maximum is. There's actually a routine that even returns the maximum location, but I just did it this way just to illustrate that it goes to all the processes. So in this case, when I compile and run, you can see that the maximum was some number, but it was on task 7, right? So in terms of the data types, so there are a lot of different data types that you can use that are already defined, right? Like, so a lot of integer, unsigned integers, characters, float, double precision, long doubles, complex numbers, and different kinds of integer sizes. And similar thing on the Fortran side, lots of definitions. Beyond this, you can also do user-defined types. That is an option. And the reduction operations, we already saw the Mpi Max, which is the maximum. Then you have Mpi Min, which is the minimum value. We also saw Mpi Sum when we did the pi example. We saw the Mpi Prod when we did the factorial example. And there are a bunch of logical options also. And this is what I meant, the Mpi Max lock and the min lock. Basically, it finds the maximum value and the location, and minimum value and the location. So that kind of gives us the pieces to do something practical now, like in terms of using it to solve a problem. So basically, when you're running MPI jobs, the idea is to partition the domain that you're the work that you have needs to be broken up into different pieces that can be done on different nodes. And typically, a lot of the solvers are doing some kind of PDE or some number of grid points, or some locality is there. So you can partition based on that. So you can take the domain and break it up. And then you can map the domain on, basically break it up based on the processes and the ranks topology. And the mapping can be based on where do you want to land on the nodes, and also the domain, and also the data itself, right? And how do you share data? You basically exchange messages like we just did. Now, if you do this decomposition in some kind of irregular fashion, then you will end up with a load imbalance, which is a problem if you're waiting, if all the processes are waiting to synchronize on something that's taking longer. Now, that can happen either because you did a poor job of breaking up the tasks. This can happen sometimes, like if you say have an unstructured mesh in like a fluid solver, it has to be partitioned equally across all the nodes, and that can be a little difficult. Like it's very easy when you have a very structured grid, like a IJK index. You say, oh yeah, just divide by the number and it's fine. But in those cases, you might have to use some partitioner like Metis that may not lead to a perfect balance all the time. The other thing that can happen is that your problem itself, your system itself is not regular, right? Like the work is not really the same on all of them. Good example for this is if you have some sort of adaptive simulation that's doing more things based on some conditional works. Like suppose, yeah, this happens a lot, like say in astrophysics, for example. You can't solve at the finest level needed to get the resolution that you need, because you just don't have enough resources. So what typically happens is they will have a coarse grid and then refine it in the areas where they need more resolution, like where a star is forming, for example. The issue with that is then, whichever processor happens to have the data or the grid section that is solving that particular star, now we'll have suddenly more work because it's refining more. So you might have to redo some of your balancing and all that. So you can end up with an imbalance very easily. But we'll start with a very simple thing. We'll start with a one-dimensional heat equation. So it's a partial derivative in time equals alpha times some second derivative in temperature, right? So, and you start with some initial condition and evolve this. So for the example, what I did is like, this is not how you should typically write a code. You should make it general, but I made it very specific in this case. Just 3 processors with 11 points so that I can show you how to do things. But in general, you should write a code that's very generalizable, so that you don't have to run with exactly the same number of processors every time. So in the numerical terms, what are we doing? We need the first derivative. So that's the temperature at the next time step minus the temperature at current time step divided by delta T. That's the coarse first order derivative in time. And then for the second derivative, again, this is Ti minus 1 minus 2 Ti and I plus 1. So this is the spatial derivative divided by delta x square gives you the second derivative in temperature in space. And you can do a Taylor series expansion to see that it's second order. So we are starting with a particular time and we are evolving it, right? So in this case, the way we've done it, it's explicit. That is, the solution on the next step only depends on the previous step. It doesn't include like all the current things. So it's very easy, right? You have Tn plus 1 equals Tn plus all this stuff. So now we are trying to break this processor into 3 processors. So what I did is have 5 points in each processor. So 0 to 4 on processor 0, 3 to 7 and 1, 6 to 10 and 2. And when we first start out, everybody has some initial condition, right? So when you distribute this, so what is going to happen is processor 0. So remember in the Pi example, I was saying, the index is going to be the same locally for all of them. So the local index is always going to be 0 through 4. So it's our job to find the global index in each case. So like in processor 0, it'll match because they're both starting from the same thing. But in processor 1, you can see the global index starts from 3. And you might be wondering, why did you do this overlap? It's because we want to be able to compute the internal points, 3 points on each processor, without having to get the value at the same time from the other process. You can exchange that after every step. So what happens is we start out, you have all the values, initial conditions, right? So you start by saying, hey, I can compute 1, 2, 3, because to compute 1, I just need 0 and 2. And to compute 3, I need 2 and 4, which are all on processor 0 right now. So that's easy, right? So you update 1, 2, 3. And on processor 1, you update 4, 5, 6. And on processor 2, you update 7, 8, 9. Now they're all updated, but on processor 0, 4 has the old value, 3 has the new value. So you need to get the new value of 3, which is sitting on the other process. Oh, sorry, new value of 4, which is sitting on processor 1 into processor 0. So that is what I mean by this here. So get 4 from 1. And then you need to send 3 to processor 1, because when you try to solve for 4 the next time, you will need the value, updated value on 3. So that's what's happening here. So basically, they are all exchanging data. And then once the exchange is done, all of them will now have the updated value. The 3 points that they already updated, and then the 2 others that they get from the boundary. Now, the boundary condition at 0 and 10, you don't have to get from anywhere, because that's actually a fixed boundary condition. So that's essentially the process. So you will have point-to-point send receives between these processes here, right? And if you look at the code, that's what's going on. So you have the initialization, size, and rank, very familiar stuff. We are now finding the global location to initialize the solution, which is just a sign X, but based on the global location, right? So that's set. So now every process has 0 to 4 defined with initial conditions. And then you just run. I'm doing 3 iterations in this case, but basically you run through this. You update the temperature on the 3 points. So I'm going from 1 to 3. Remember, the local index will go from 1 to 3. And then doing the send receives. And then at the end, you'll notice I'm doing something here with the output. I am basically using the ID and finding the character that corresponds to that, so that you will get data 0.dat with all the data from 0, data 1.dat from all the data from 1, and so on. So quite simple setup, domain broken up like that. So to compile this, let me go to this. This is in the domain directory. So let me go there. So let me see if I have any questions. So I am setting up the MPI first. And you will see there is a fixed form flag here. It's because I use the fixed form, but I'm compiling an F90 using an F90 code. So, and then submit the job, right? And I'm going to add the account for myself. And so you'll see it will create create the 3 data files at the end of it. But what you'll see is processors running the first iteration, sending, receiving overlap points, running the second iteration, sending, receive, and then third iteration, sending, receive, so on. So, and then at the end, it writes out these 3 files. So you'll see the data from each. So what I did in each case is print the local index, global index, and that, right? So now let's go back here and look at the solution. So this is the sample output. So what I did is put each of these files in a different box so you can compare. So you can see if you go match the global index, then you should be able to see if your solution is right. So I global equals 3, the temperature is 0.804 after 3 steps. Go back to processor 1, which again is the global index of 3. You see 0.804, whatever, the whole thing is, right? So you see that that matches, and then you can confirm that 4 also matches. Those are the 2 overlap points there, so you can see they are matching fine. And this actually is easy to match visually. Like if you plot like the solution from all 3 together, if there's a mismatch, your eye will pick out the mismatch because there'll be a slope difference, and that's very easy to pick out. Now, there are, I don't go into them today, but there are MPI routines that actually let you print out to one single file by combining the data from all these processes. So you don't have to explicitly write out 3 different files. You can write out one file, but each process will write to a particular piece of the file. And that's called MPI IO. And that can be a talk by itself. So I didn't include anything, but you can go look for resources on that if you need to. So in general, like if you have very few tasks, like if you have 4 tasks or 8 tasks, it's okay to write different files from each node, as long as you are able to match and manage the solution. Or sometimes what people do is if the data set is not too big, like say, you have a few 100 megabytes to write out, you can send it all to one process and then write it out from there, which is also fine. Like if you look at a better code like WRF, they have all options. Like they have an option to send everything to 0 and write it out. They have an option to do parallel IO with file per core. They also have an option of writing a single file. So it's like everything is on the table. But when you get to like really large numbers, like say you're running with 16,000 tasks, you don't want to be writing one file per core, because a lot of file systems can't handle millions of files. Especially if they're in the same directory, it causes a lot of problems because it's a metadata overload. So in such cases, it's very important to do some kind of collective IO. And even in collective IO write-outs, there are options to buffer and write from a smaller subset of processes. So you don't write from 16,000 processes straight into one file, because that also will cause problems with contention. So what they have is buffering options that will, say you have 16,000 processes, you can buffer it down so that only like 4,000 of them write, or only 1,000 of them write at the same time. And that's enough to kind of get around any file system problems. But the key is to keep that in mind. Like you can overwhelm a file system very easily if you're not careful with IO, especially if you're doing file per core. Like one example of this is the code OpenFOAM, which is an open source CFD code. By default does this, where it writes a file per core. But not only that, they do file per core per variable. So like, if they have 5 variables like pressure, velocities, and something else like a temperature or something, they will, a density usually, they will basically print all of them out in different files. So you can imagine if you run with, and then they do that at different time steps. So you can imagine if you're writing every 10 time steps and you run for 10,000 steps, now you have 1,000 factor there. Then you have, say, 256 processors. Now you have 256,000, and 5 variables, you're talking 1,000,000 files plus. So, and they all end up in like the same file system. It can cause problems. So it's good to remember about IO when you start scaling up. Now, what we saw there was a one-dimensional grid and a simple one-dimensional partitioning of the data, right? But there are obviously, when you run real problems, you're not going to be solving one-dimensional problems. So this is some examples of decomposition when you're doing 2D problems. And there was a comment, sorry, in the chat that says, sounds like an issue with synchronous checkpoint restart. Yes, so checkpoint restarts can be an issue if you're doing it with from a lot of files. sorry, a lot of tasks, and then you write out like too many files even from each task. Yes, that can be an issue. So the other thing, so there are solutions to that also that are a little bit clever in terms of how they do it. So there is a library called Scalable Checkpoint Restart out of Livermore, I think, where they can layer the checkpoints from local scratch onto global scratch. So when they write out during a run, they will write out to local scratch for the most part, so that if the run crashes and the local scratch is still there, you can recover from that. And they have options to sort of erasure code it so that you don't, you have multiple copies of it. So if one node dies, you still can recover the entire checkpoint from the rest of the nodes. But yes, that can be an issue. That shows up in, especially for large cases, and you'll see that on large scale runs on big machines like Frontera, for example. You might have to be very careful about checkpoints. So yeah, so going back to the decomposition, so here we just have a 2D matrix, and say you're doing it with 4 tasks. One thing you could do is just do a column wise, right? Column 1 goes into task 0, column 2 goes into task 1, and so on. That's one way of decomposing it. There's also another way of just saying, hey, or you have only 2 tasks, then you do submatrices, right? So yeah, you take the first 2 columns and stick them in task 0 and the second set into task 1. But usually you will have a much bigger matrix, and you might be doing a 2D decomposition. So this is an example of that. So say you're doing a matrix multiplication and you just do a 2D Cartesian mapping for the processes. So you map the processes into a 2D grid and also do a mapping of the data. And there are MPI functions to let you do this kind of Cartesian mapping. So it's not that difficult to do once you know the right functions to use. And then basically you're allocating space on each MPI task for the subarrays of these things. So like, for example, task 0 might have this space, task 1 will have that, so on. So when you do this matrix multiplication, you can imagine that you will need to exchange A and B data as we need, as you go along. So that was basically all the pieces you need to kind of take a problem, break it up into different domains, use either point-to-point or collective communications as you need to run these things. But when you do that, and if you just do a naive implementation, you might see that, hey, it works okay when I run with 4 cores or 8 cores, or it scales okay to maybe 64 cores. Then I go to 1,000 cores and everything just goes to hell because the communication takes too long, and you end up spending more time in communicating data than actually computing data. So there are considerations there. So one I already talked about. You can overlap the communication with computation, right? So you can use the non-blocking stuff that I mentioned. So going back to this problem, see, technically, if you go back to this processor example, 1, 2, 3 can happen without having to get the values. I mean, you can start by doing the value at 4 and 3 and then sending them off with a non-blocking, and then do the rest of the domain, right? That way, what happens is while you're spending time computing 1 and 2, 3 and 4 would have gotten communicated. So that will overlap the thing. So especially if your compute piece is much bigger, I mean, that example had only 2 points, but say you have 10,000 points and you only sent 2 of the boundary points across or 4 of the boundary points across, depending on what accuracy level you need. The rest 10,000 computes will easily take more time than the communication time for sending 4 pieces of data. So if you do a non-blocking, then you'll completely hide the communication. So that's one way of doing it. And there's actually a code in-house, I think the Southern California Earthquake Center, which some of the SDSC folks were involved in optimizing. They used a lot of this kind of approach where they completely overlap the communication with computation and get near perfect scaling going out to hundreds of thousands of cores, because you're essentially hiding the communication. The other thing is try to minimize the surface to volume ratio, because the surface is what you're sending across, right? The surface between the tasks. This is now talking about 3-dimensional kind of data sets. So that you're not, you're only exchanging the ghost cells that are on the boundaries. So if you minimize that surface to volume, then you'll have more compute and very little communication. So that's one thing you can do. Sometimes it's, if you can avoid communication by computing more, that might be useful. Like if the compute is a quicker thing than the communication, that will work out. You can also double the sizes of these ghost cells and communicate every other time step. This is a little bit of a tricky maneuver, but you can do that. You can also find algorithms that don't need as much communication. So that's another thing. I think I'm going to just skip this one, but basically this is again overlapping compute. Now, one of the key things that you have to think about when you're running with MPI and trying to find out why something is not working as you think it should, scaling wise, is to look at profiling your MPI job, right? So there are always tools available on the system. We have several options available on Expanse. We have MPIP and Tau. These are useful if you're trying to isolate performance issues. So what the tools can do is give you info on how much time is being spent in communication, depending on the tool, actually. Like, Tau has a lot more options and can give you a lot more information. Beyond just communication, it can also tell you what the code is doing on the node. So in general, you can find these scaling bottlenecks. So I have an MPIP example. Again, this is in the miscellaneous folder. And I used a different set of compilers here because we have MPIP only with these compilers. So I can go try that. So let me go to the miscellaneous directory. So I'm doing a module reset and using loading GCC OpenMPI and MPIP, which is the profiling tool. And in that directory, I have this compile underscore profile dash readme. You can use that to get the compile line. So I'm going to grab that compile line. And get the profile information there. So once this runs, you will get a file, and I think I should have shown you that file before. You get a file like this, right, which has the profile in it. Which this is a useful thing in general, also to kind of log like where things ran. So it has information on which nodes were used. This was a small three task job, so I stuck it on one node. So that's where the 129 is. It tells you the start time and end time of the job. This is like takes less than a second, I think, so it's too quick. But you can see it will break down based on the MPI time on each task, the MPI percentage. So you can see overall the MPI percentage was very small, like 4%. It also gives you the call site information. And if you compile with debug flags, you can probably even get the line number info. But basically, you have the call sites, like what calls were being used. It will tell you like the aggregate time in all the calls. So if one particular call is taking too long, you can figure out. And this MPI percentage is the percentage of all the MPI part of it. And then it tells you like the message size and all kinds of statistics, basically. Now, tau can go a lot further and give you like the complete trace of how the communication happened. And there are tools like Alinea Map, which also do similar things. One thing to keep in mind with these tools, like the reason I showed you MPIP is because MPIP is the most lightweight thing. And you can find out very quickly because it's showing you the MPI time per task if there is some imbalance. Like if one of the tasks is doing a huge MPI weight, you should go look at, oh, why is this happening? Right? So it's a quick way of finding things. And it's also a quick way of finding if your code is constrained by communication or something else is going on, right? So that's a good quick tool. But if you want to go further deeper into like what is happening, then you can use something like Tau or Alinea Map. Now, so that's kind of the profiling side of the story. There are also like a lot of complex routines in MPI that I showed you just the very basic number of things that are needed to show like a simple MPI code, but there are lots of options. So like as I mentioned, there are derived data types. You can have user-defined reduction functions if you want something interesting that's not supported already. As I mentioned, you can have communicators. So one thing that some codes do is they don't write from all the processes, but they have like, say, you have 256 cores. They may add like 16 cores whose job it is to just write do IO. So there are ways to do that. So that's some place where you might use a separate communicator for the IO piece, because then you can do collective IO from just that communicator. So there's parallel IO options. There's one-sided routines, which is RDMA stands for remote direct memory access. This is what I meant by writing directly into the remote memory instead of having to go through the buffers that I was talking about, system buffers. That obviously means it'll be faster, lower latency. So that's and nowadays a lot of the network adapters are very smart and they have their own compute possibilities on the adapter. In fact, now Mellanox has a lot of compute in the network. So like some of these reduction operations and the sum operations that I was talking about, they can do that in network or on chip, on the network chip, which means that the CPU is not spending time basically doing those things. So there are all kinds of complex things that you can do. So there's MPI standard, 3 standard has over 400 routines. So you can imagine. So I think the last part of the talk, I'm going to talk about hybrid MPI and OpenMP jobs. So we talked about MPI today. We talked about threaded jobs last week. So there's, so Maria, you mentioned the question about the multiple communicators. The IO is one example where you would, it'll be useful to have a communicator that is dealing with that piece. There are other codes that do it too, and I can't think of one off the top of my head, but I can maybe drop a note if I find a code that's commonly available, so you can look at it. But if you're looking for the complex IO setup that I was talking about, you can look at the weather research code, the WRF code that does do the IO separately. Has the option to do it. You don't have to do it that way, but that's one thing I can think of. So in this, so on expanse, since we have 128 cores per node, and if you have, say, like 32 nodes, you can have a lot of processes. You can end up with 4,000 processes very easily, right? So if you have 4,000 cores, you probably don't want to do pure MPI collectives, because if you do a collective with 4,000 elements, 4,000 tasks, you're going to have a lot of buffer space that you would need. It will complicate the MPI traffic and bottleneck sometimes because of that. So, so a lot of times when you have nodes with a lot of cores, what people do is hybrid MPI OpenMP jobs. So what they might do is they might launch 16 or 8 MPI tasks on the node, and then each MPI task might have 16 threads or 8 threads or something like that. So you still use all 128 cores, but you have this hybrid setup where you have MPI and OpenMP. Now, that can lead to some interesting issues because of the architecture. So let me talk about the Amd Epic architecture on Expanse. So what you have is this is one socket of Expanse. So the one of those AMD processors which has 64 cores. So that's broken up into 8 core complex dies, and each of these core complex dies has 8 cores in it. So that's how you get to 64. And there is an IO die that ties up all these. So there are 8 memory channels per socket, and then each of those channels, you can figure out how you connect these to the CCDs. So that's where the complexity comes in. And so typically memory and IO can be abstracted into quadrants. So you can grab one of these quadrants which has the some of the IO channels and basically the memory, right? So you can have 2 DIMM channels and 32 IO lanes in each quadrant. And that's how Expanse is set up, by the way. So you will see 8 NUMA domains on a node, 4 in each socket, basically. And that's what's happening there. So you can already imagine, there's non-uniform memory access, right? Because of this setup. Now, in a core complex die itself, there are 2 core complexes which share L3 caches. So you can see the circled thing here, where you have a CCX, the core complex, which has 4 cores, 4 of these Zen2 cores, and they all share a 16 meg L3 cache. And if you look at the latest AMD chip, which is the Milan, they actually, all of them share a bigger cache. I forget what the cache size is, but it's bigger. So again, there's another memory architecture here, right? Memory hierarchy here. And then each core has its own private L2 cache, which is a different. Now, so one thing you can already think of is like, hey, if you're doing a shared memory thing, maybe you want to stick all the threads in one CCX. So you have a MPI task per CCX, but then the 4 threads share an L3. That might be useful, right? So that's one plausible reason why you might have to think about how you lay things out. And also you might want to think about laying it out at the CCD level, because you have the 2 memory channels. You don't want to oversubscribe one memory channel and not use the other memory channel properly. So layout will matter a lot. So as I mentioned, it can be broken up into 4 quadrants. And you can say how many NUMA domains per socket you want. You can, if you want, you can put all of the channels into one NUMA domain, but performance-wise, that might not be the best for HPC. So for HPC codes, most codes are very, I mean, they've been developed over years to kind of handle NUMA configurations. So a lot of the HPC codes can manage this very well. So our default setup is to have 4 NUMA domains per socket on expanse. So in the NPS 4, basically it's 4 quadrants, and so you have 2 CCDs in each. So that's 16 cores in each of the quadrants. And the memory, there are 2 memory channels associated with that. And your network card will be on one of these quadrants. Actually, one of the chips will have one of the quadrants with the PCIe route for the device, for the network device. So that's another thing to think about, like when you're doing the layouts. So, and same thing goes for any disk that is local, right? There'll be a route for that one also. So it's very important to lay the processes out correctly and also pin them, because if they're moving around, you're going to be going across a lot of NUMA domains. So, so there are lots of ways of doing this. All MPI implementations have affinity options, like OpenMPI, for example. You can say map by L3 cache. So it will then lay out based on those L3 cache locations. And L3 cache, if you remember, is at the CCX level, right? So OpenMPI has a flag that recognizes that, hey, I can lay it out this way. And then Intel MPI has these options of doing pin domains, which again achieve similar things. You can also combine, some applications have pinning options. For example, Amd has options to do CPU affinity with a mapping, explicit mapping that you can use. So you can see here, we split it up into 2 32 core maps on each node, or sorry, in each socket. So you have a total of 4 MPI tasks on each node, and then 32 cores being used for each, threads being used in each. Actually, you'll notice it's only using 31. It's because we use 4 of them for communication. MPI has, Amd has options for setting aside communication cores. So that's what we are using here. So you can see it can be pretty complicated in terms of how you lay things out. So in this case, what you're saying is map by PPR processes per, you're saying 4 per node, right? That's what's going on here. But sometimes it's not that easy to set all this up yourself. So what we did is and this is a lot of work by Manu Santaram, who set up all these IB run scripts on expanse. So what we are trying to do is make it easier for you to do some of the binding. So what IB run will do under the covers is find all the commands that are needed to set the binding correctly and set it up. So so you can do you can run with affinity, saying IB run affinity, and then you can give it some hints and options that I'm showing below, and then the executable, and then whatever the executable options are. So the affinity options, there is a scatter option, which will scatter across all the NUMA domains in cyclical fashion. Then there's a scatter CCD. So you scatter across CCD domains. So for example, when we are doing 1 MPI task per CCD, this is probably one way of doing it, right? You can cycle through all the domains, and each CCD will get 1 MPI task. You can do it at the CCX level. You can also do blocks of ranks on each so that they're consecutive. So lots of options, basically. And let's go into some of the details. So this is kind of the guideline for the layout that I'm going to show in the upcoming slides. So think of it as basically a CCX next to each other, and then the CCD combining those two. And all 16 of these end up in one NUMA domain. Remember, we are doing NPS 4, so you have 2 memory channels per quadrant, and that is in one memory access NUMA domain, right? So So let's look at this. So in this example, so what we are doing is IB run without anything, right? So by default, it will just scatter across all the NUMA domains. So that's what's happening here. Now what we are saying is, hey, scatter, but and this is with 2 nodes, but we want a block of 3. So what it will do is put 3 on the first NUMA domain, 3 on the next NUMA domain, and it's also going to use multiple nodes, so it's going to do the other 3 there, right? So that's how that works. Now in this example, what we have is CPUs per task set to 2. So the previous one, the CPUs per task was 1. So this would be a hybrid case where you have MPI tasks and then each task has 2 threads. So now you can see it picked up 2 threads in the same CCX and then laid out the tasks again the same way. Now we are saying scatter CCD. So again, it's now putting it in different CCDs, right? So that was the first CCX. So it basically put it in scattering across multiple CCDs. And then the scatter CCX would just pick one from each CCX. That's what's going on. So you can see with IB run, you can control exactly how the processes get laid out. And notice that all we are doing is loading the MPI and using IB run. The module load SDSC is what puts IB run in your path, just in case you have. One thing I want to point out is the reset. So you should do module reset instead of a purge, because then it keeps the slum module loaded and it resets to the default on that node, basically. So now I have a scatter CCX option, and I also did a CPUs per task is 4. So you can see now that, and this output is from HTOP, by the way, which is a really nice thing to do, to look at how the things got laid out, all the tasks. So you can see this is a code that is hybrid. It's HPL is a high performance linpack, which is basically one of the benchmarks used to see how fast your computer is running. So it does a simple matrix operations. So then there are in this case 32 MPI tasks, and excuse me, I'm gonna take a step. Hold on. So you can see the first task landed on core 0, which is HTOP labels starting from 1, but that's basically core 0. The next one went to 4, right? Or basically the 5th process. So, and these are laid out in the CCX manner. So basically, you can see that the threads are sitting on those. So I deliberately caught it when the threads were not fully utilizing the core. So you can see the difference basically of all the different MPI tasks. So everything that says 100% is where the MPI task is, and then the threads are there basically. And you can go confirm this by looking at the PS output. So you can see anything that has the same process ID. So like say, for example, 82667, all of them are basically the same process. So you can see the master thread, which is going to be the MPI task, and then which is on 0, and then the other 3, right? And so on. So you can see all the tasks. So that's how things are laid out. So to basically to summarize, the AMD processor and expanse has 4 NUMA domains with 16 cores each. And you have like 8 core complex dies. And then with 2 core complexes in each CCD. And the 4 cores in a CCX share a L3 cache, so that's one thing to remember. For any hybrid MPI, OpenMP, MPI pre-threads codes, it's really important to lay out tasks correctly. So there is the affinity flag and the IV run that I was talking about. One thing I didn't talk about is the Slurm affinity production script, and this script is mainly for the pthreads cases. This is because pthreads are not that easy to control with external environment variables. Either the code needs to recognize and do the right thing, or we have to manually change the binding once the thread is launched. You can't do it ahead of schedule. Like OpenMP, you can control exactly where the threads land, but you can't do that with pthreads. So we have this script that basically what we do is we launch the job with the pthreads, and then this script can go and change the affinity to the right locations for all the pthreads, and that works okay. And you can drop us a note if you need an example of this. I think one of the codes that we had to do this was RacksML, if I'm not mistaken. And if something's missing and you want to try something else, do let us know, because these things are being updated and we can change things as needed. So the last thing is your homework. And I haven't put this in the task list, but I'll put that in. But just try to write an Mpi code that does a matrix vector multiplication for a Hilbert matrix. And if you're wondering what an Hilbert matrix, it's a square matrix with the elements that are unit fractions, like 1 over I plus j minus 1. And the good thing is that there is an analytical result. So basically you can get a very quick check on whether you got the right answer. And I think I'm not sure if you got the same homework for OpenMP, but if you did, you can compare those two. But if not, try to do a speed up study and see how efficient your MPI implementation is as you go to 64 cores. So I already talked about some of the domain decompositions for a 2D matrix, so you can look at those and see if anything helps, or you can do some research and find out what's the best way to do a matrix vector multiplication in a parallel way. There should be lots of examples for this. I also want to point out there are lots of excellent tutorials on MPI. There's a tutorial from Livermore, which basically has all the components that I talked about, but also a lot more examples. There's also a set of slides for more complicated examples that you can look at. And they also have an OpenMP tutorial. I think Marty might have given you this link last week. There is MPI for Python if you're trying to launch MPI via Python. It's called MPI for Pi, and I have the documentation there. Now, if you want to use this on Expanse, you have to be a little careful. If you're on a single node and doing MPI, it's not too bad. You can use like an Anaconda install of MPI for Pi. But if you're doing multi-node, please make sure that you build the MPI for Pi with our MPI, because otherwise you're going to go over the Ethernet and it's not going to be pretty. You're probably going to get bad performance, or worse, might cause timeouts and all kinds of things. There's an OpenMPI user guide and an Mpi user guide, and I have them there mainly so that you can take a look at some of the tuning flags that are there. Like especially the Mpi user guide is very good at explaining all the tuning options that are there. So you can go look at that. Mpi also has a kind of a best practices page that they have some tuning examples for like common applications that are used, like Amber, for example. So you can take a look at those. So I think that might be my last slide. Yep, I think that's the last slide. So hopefully that wasn't too rushed, but there's a lot of info to absorb. So please try out the examples and send us a question if you have any problems. But I think you should be able to run most of these on a single node. One thing I didn't mention is that you can use MPI even if you're running single node, especially when you're doing like, when you have a node with 128 cores, it shouldn't be a problem testing like a 64 core thing on one node. In fact, it's quite interesting to see how the binding changes your performance when you're doing single node. You'll see that you might get pretty varied performance depending on where things land. Also, I think the thing that you should look into is like OpenMPI, for example, has shared memory options for MPI. So you would make an MPI call, but the MPI, and it's the same with MVAPage. They're both MPIs are smart enough to realize that, hey, it's on the same node. I don't need to send it through the network and get it back. They will use a shared memory option. Like, so for example, MVAPage might use something called cross memory attach, and also they use XPmem, both of which kind of help with performance of codes on a node. And OpenMPI has its own implementation of shared memory stuff for on-node MPI. So you can play with all those things. So I see a question. It says, when we did OpenMP, the CPUs were tasked for number of threads. No, actually, so in MPI, the task per node is the number of MPI tasks. The CPUs per task will still be the number of threads. So if you're doing a hybrid code, like say you want to run 32 MPI tasks and 4 threads per task, what you would do is task per node equals 32 and CPUs per task is 4. Then that way Slurm knows that you're doing a hybrid thing. And by the way, Slurm is like SRun is smart enough to lay out things correctly also. There are options for SRun which also let you do affinity and kind of lay out processes correctly. So it's very important when you're doing a hybrid case to make sure you do task per node and MPI, match the MPI tasks, and CPUs per task match the OpenMP. And also going back to the question, make sure you don't set the, like don't do task per node as 1 and thread CPUs per task as 128 and then do an MPI job with 128 tasks, because then it'll stick all 128 of them into the task 0th core, and you will have really poor performance. so yeah, so in short, the task per node corresponds to the MPI, and then CPUs per task corresponds to the number of threads. Any other questions? Let's see. Great. And Mary had the link to the talk. Thanks. All right. Yeah. So get on the machine and play with the examples. And like I said, those tutorials have a lot more examples, so you can get those and try them out too. And there should be lots of material online if you're poking around and testing things. And the other thing I want to.
Sorry.
I think she just said thanks to the other one.
No,
somebody. I think question. Yeah, sorry, about course. The use of Slurm of course versus CPUs. If you
so it's a little yeah, they call it CPUs, but they're essentially meaning cores there, because CPU by like CPU, typically people will think a processor which has a lot of cores, right? But that's, yeah, it's a little confusing there, the way it's laid out. And it's even more confusing when we have hyperthreading turned on. We don't have it on, but if you have it on, you're going to have 256 cores in quotes, because it's going to look like there are 256. Yeah, so, but we have it off on Expand.
So how about hyperthreading that Carolina is mentioning?
Yeah, that's what I meant. Like if you have hyperthreading on, you will have 256. As far as Slurm is concerned, it will see 256 instead of 128.
Oh, I see.
Yeah.
Okay.
But we don't have it on. So your physical cores and logical cores are the same on our machine. But if you have hyperthreading on, you will see 256 logical cores. So so you'll get a lot more confusion, especially when you're binding things. You have to be very careful, like to not oversubscribe the same core, basically. Great. All right. Thanks, everyone. And yeah, let us know if you have any questions.